In Chapter 3, Networking Language, that's our focus. After completing this chapter, you're expected to be able to describe the components of the Media Access Control MAC address. Understand the difference between connection-oriented and connectionless protocols. Identify common services and ports. Explain how domain name service works. Classify protocols as routed or routing. When it comes to addressing, keep in mind that there are two types of addressing, the physical and the logical. The physical addressing happens at layer 2, which is the data link layer, while the logical addressing happens at layer 3, which is the network layer. The physical addressing depends on the types of network being used, for instance, Ethernet, local area network, while the logical address depends on the protocol suite used in the networking, for instance, the IP address, Internet Protocol. Our focus for physical addressing, it is the Media Access Control address, MAC address. Physical address refers to either a memory location identified in the form of a binary number or immediate access control address. So our focus is to understand the components of the MAC address. However, keep in mind that the MAC address is managed and allocated by the Institute of Electrical and Electronics Engineers under the purview of the 802 Standards Working Group. The MAC address must be unique among all the hosts to function properly on a network. It must be unique. No two devices have the same MAC address. The MAC address is assigned to the host network interface card, NIC. The host uses the address only for local segment communication. Yep. At the local area. The MAC address comprises of 48 bits. 48 bits. Look at the diagram. 48 bits expressed in hexadecimal notation. Typically 6 groups of 2 hexadecimal digits. You could see 1, 2, 3, 4, 5, 6. Each of this contains 8 bits, and if you multiply that, right, it gives you 48 bits. So 8 bits per grouping. The address can be written without separating symbols, but it is more common to write it using hyphens. You could see in the diagram on figure 3.1. You could either use hyphens or you can use colons. On occasion, the MAC address is written in 16-bit groups with a period separator. However, that notation is considered less official. Yep. A MAC address can be universally administered address. That is one that is managed and assigned to a device, network interface card, by the device manufacturer. Yep. The first 24 bits of a MAC address constitute the organizational unique identifier. Each device manufacturer is assigned a unique organizational unit identifier or multiple organizational unit identifiers, depending on the manufacturer's volume of equipment. Yep. Like says the MAC address, its first characteristic is that it's unique. because it's used to identify a device, a specific device. No two devices will ever have the same MAC address. It's like a social security number. Then the last 24 bits is the serial number. Look at the diagram on figure 3.2. Like the first 24, right? That's the organization unit identifier. And the second 24 bits is the serial number of that device. When assigning MAC addresses to NICs, some manufacturers store them in a ROM, random only memory, which serves as a storage. These addresses are often called burnt-in addresses, or hardware addresses, because they cannot be changed. Burnt, which means it's been embedded. It's like a social security number. I repeat, if you have a social security number, rarely would it be changed. I know in this case, I'm not trying to compare, they aren't apples to apples, but it's kind of a social security number is meant not to be changed. On rare circumstances will social security numbers be changed. MAC addresses, they don't. MAC addresses are not always assigned that way. However, often software is used to set up device NICs and interfaces. That will require software to be able to set these network interface cards and interfaces. They're being controlled by software. The system administrator can change the MAC address, yep, if warranted. Like I said, just like social security numbers, they are meant not to be changed, but can be changed on rare circumstances. The logically administered address type is less common than the MAC type, but the LAAA assignment method is useful if duplicate MACs create problems on the segment. The diagram on figure 3.3 just shows us logically administered addresses scheme. That is a component of MAC address. It's worthy to know that an entire Ethernet frame that is sent onto the network segment from a network interface card has the address of its own network interface card. Also known as the source address, because it's the sender, right? So it has a source address. And the address of the host to which the data are being sent, the destination address. If the host is broadcasting a frame to all computers, then the destination address is all the F's, which signals every host to look at the frame. The diagram on figure 3.4 kind of give you a picture of an Ethernet frame. When we looked at the 7 layers of the OSI model, when we talked about data link, we talked about frame, Ethernet frame, and we did mention this. So I don't expect this to be strange to you. So what you have to understand here is data sent from the application are housed in the data field. That's a data field that range from between 46 to 1500 bytes. The frame check sequence, the FCS, which is composed of 4 bytes. What does it do? It verifies that the destination received the entire frame. And that's one of the things that is very important with TCP connected connected network because it checks packages and ensures that there's no error, there's no drop off package, and ensures to put things in intact. This diagram is self-explanatory. We've got the preamble, we've got the destination address, the source address, the length, and all that stuff. Just read that for a better understanding. Now we're going to step into logical addressing. The key things to keep in mind here is it takes place at layer 3, the network layer. And it is based on the relevance of an address in the network. So the protocol, right? Although physical addressing is used only within a single network segment, logical addressing, on the other hand, is employed end-to-end, regardless of the number of network segments that may separate the source and the destination. Logical addressing, which is relatively uncommon because it works the same across a router, an internetwork, or the internet. The source computer finds the destination host logical address. You can see this diagram. That's it. In other words, it's referred to as address resolution protocol, where the source computer finds the destination host logical address resolution protocol. A logical IP address is structured with the goal of locating every individual host on the internet network. A good number of times we've used the US Post Office example as kind of like an apple-to-apple situation of how this process works, where a letter is sent from Washington, D.C. to a recipient at this address. After the letter is mailed, right, the system starts breaking down the address and starts moving the letter closer to its destination step by step. It looks at the zip code and the state to indicate the large area surrounding the letter destination. Starts routing it closer to that area. In this case, the letter would have to be loaded onto a plane or a carrier if it's ground and sent across the country. In IP terms, it's just kind of that letter or that data. That letter will be referred to a data that is leaving the local area network and embarking on a journey over a wide area network. After the letter reaches the destination, which in this case is the state of California, the mail system sends it to the hub nearest to its destination, like the city. Starts taking it down to the city, to that local area, right? If you order stuff online, and track them, you see how those packages move from one state to the other and closer to your location and being transferred over to USPS centers, and they re-encapsulate and keep sending it closer to your location. In IP terms, right, this is exiting the wide area network and entering the network of the entity hosting the destination computer. The mail system next assigns the letter to a truck that will carry it to the correct street within the city. I mentioned that in one of the examples that I used to explain a process similar to this in chapter 2. In IP terms, it is the equivalent of accessing the router associated with the destination network segment. Finally, the carrier takes the letter to the specific address of the house or business. In this case, the house number and the street. This correlates within the specific IP address of the destination host. It's important for you to know that IPv4 addresses have a hierarchy design and framework. Its addresses are 32 bits and they are expressed using a dotted decimal notation format. Base 10 numbering. Period separated 32 bits into 4 groups. 4 groups of 4 bytes each. So that's it. So examples of IP addresses. It's composed of 32 bits. We're going to be delving into IPv4 a little bit further down here. But before we go down, let's look at address resolution protocol. The Internet Control Message Protocol used within the TCP/IP suite allows devices to send and receive error messages and operational messages. It includes the well-known ping and traceroute programs which test connectivity between hosts. In summary, an address resolution protocol, which is one of the protocols in the data link layer, is just basically used to be able to find hardware addresses of a host from a known IP address. Like I mentioned, 2 programs are involved in making this accomplished. You've got the ping, which lets a network device query another device to determine distance, check for blocks, and determine whether a destination is alive. It's just kind of like a welfare check where somebody calls your telephone number to kind of find out, hey, is this person awake, or is this person, I haven't heard from this person for a while. It conducts the test by pinging echo request and echo response messages within the ICMP protocol. If you're not familiar with the ICMP, it just simply means Internet Control Message Protocol. The other program that exists within address resolution protocol is traceroute. It functions just like the ping, but it goes further. It has the capability of checking every hop or router between the source and destination. For instance, it doesn't only find the location of the device, but it finds all the routes that it connects to. If only an IP address is known, the address resolution protocol can be used to identify a destination's host MAC address. Yep. It will ping you and get a response. The diagram on figure 3.5 shows a ping utility testing connectivity. So if you have a computer, right, you just go to the command interface, you open it up. If you have an address of that device, you type ping, log in the address, and hit enter. It's going to send kind of like an echo request. Poking your door. It's like you knocking at somebody's door and then to wait if the person is going to respond for you to know if the person is in the house or not. Yep. You have the person's address, but you don't know if the person is there. So, right. You send an echo request. And if you knock, and the guy says, hello. If you say hello and he says hi, then you know, hey, there's somebody in the house. That's basically what it is. You ping, and the computer responds like, okay, yeah, that was the right address. I heard the voice. Sounds like what I'm looking for. The diagram of figure 3.6 depicts a locally administered address scheme So in this case, it's not only about getting an echo request to know if the person is there, right? But you really want to know, you have the person's IP address, but you want to know the person's MAC address. There you go. Let's look into protocols. IPv4, Internet Protocol version 4. It's one of the most common protocol. We touched a little bit earlier on. It's important for you to keep in mind that the IPv address contains 32 bits of 4 bytes each. The network ID portion of the IP address is always to the left part. There you go. Whereas the right part of the address is always the host ID portion. So the left part is the IP address, and the right part is the host ID portion. Keep that in mind. Unlike the MAC address, right, we have the OUI on the left, and we have the serial number on the right of the device. So 32 bits of 4 bytes. Another thing for you to keep in mind here with IPv4 addresses is the various classes. The diagram on figure 3.8 lays down an IP address class and its definition. Class A, specifically for enterprise and organizational addresses. Class B is for mid-sized enterprise and based on numbers of hosts. Class C is used for small enterprise and homes. The D class is kind of reserved for a type of communication called multicast. And the E class is reserved for research and future use. Note that the class of an IP address can always be determined by looking at the first number in the octet at the far left. Look at the diagram on figure 3.9. Yep, the far left. In this example, you could see how it says if all 8 bits are zeros, then the range starts at 0. If all 8 bits are ones, then the range ends at 255. Minus 1 because the counting starts at 0. Figure 3.9 shows us the classes of IPv4 addresses. That's what we just explained. Yeah, so familiar with that. When using IP addressing, it is much easier if the values are 8 bits of placeholders, and the addresses are more often added from the most significant bits rather than the least significant. IP addressing is shown in figure 3.10. Diagram in figure 3.10 gives you a visualization of bits to decimal. It makes it very easy for you to calculate, just by looking at it. It's got its full 8, right? We all know it's 255 range of IPs, and as it goes down 7, 6, the number changes. This shows them how to memorize the power of 2 for binary. Math can make the work and troubleshooting networks much easier. This is kind of like a quick review. 2 to the first power, 2 to the second power. It goes and goes and goes. The diagram on figure 3.11 determines network and host based in IP address by class. You can just read about IPv6 address, a better understanding of this course. Look at the diagram in figure 3.17, connections of messages, just for a better understanding on how things operate. However, let's focus a little bit on connection-oriented protocols and connectionless-oriented protocol, just for a better understanding of this course. And you might as well just focus on this a little bit, because you might get a question come out from here. So usually there are always questions about which protocol is reliable and which protocol is not reliable. Or you might get a question like, hey, which protocol would you use if you're doing video streaming and stuff like that? So, which is usually UDP. Though it's not reliable, but it is able to route videos for streaming without any high latency. When it comes to connection-oriented protocols, first thing you have to keep in mind is that it is the TCP that's involved, Transmission Control Protocol. And also, the characteristics of that TCP is very important for you to keep in mind. TCP is connection oriented and provides delivery of a stream of data between applications running on hosts that are communicating via an IP network. Connection oriented in this case means it's reliable, it puts things in order, and error checking. You want to keep that in mind about TCP. And you also have to be aware of where it provides its service. It happens between the application program and the internet protocol. TCP provides host-to-host connectivity at the transport layer. You got to keep in mind the layer that it's at the transport layer. These are the three things that are involved in that connection. You want to be aware of what it does. So items such as IP fragmentation, ordering of the packets, retransmission of lost packets are all handled by TCP and are not known to the application. That's why it does error checking. The transport layer, TCP handles all handshaking and transmission details and presents an abstraction of the network connection to the application, typically through a network socket interface. If you're curious what may make IP packets lost, duplicated, or delivered, it could be due to network congestion, due to traffic load balancing, and due to unpredictable network performance. And TCP does detect all these problems, and that's why it does request retransmissions of lost data, rearranges them out of order, and even helps minimize network congestion to reduce the occurrence of other problems. The diagram on figure 3.18 shows us a TCP header section. Source port, destination port, sequence number, acknowledge number, data offset, reserved, checksum window, and you've got all those. See something like finish, reset, push, post, all the stuff. These are the definitions, descriptions in the bottom. You can just read this to kind of understand what is involved at that level in the header. Windows, checksums, you can just read that for a better understanding of this course. You can read them. You could also read this to kind of understand the three-way handshake. Sing, act, and act. Just pretty explanatory on how handshakes occur within the TCP. The three-way handshake is like one of that kind of a thing where network engineers or students of network and infrastructure are required to have an understanding how TCP does the three-way handshake. You signals, you negotiate, you synchronize and sync and acknowledge, and then you acknowledge, and then you deliver, and then a connection is established, and then you transfer the data. The diagram on figure 3.20 just depicts some of the well-known ports, numbers, and description. Just read these ones and kind of understand some of those common ports that we do have. Especially something like the port 25, simple mail transfer protocol, deals with mails, and 42 host name. I think one of the most common here is the 80, which is the HTTP. Everybody does browse out there, and they reach out to the internet. Read that for a better understanding. These are the common ports. If you're a network engineer, you're required to know these common ports. It doesn't mean that you can configure some other ports to do the same thing or to tie into some of these services, but these are the common or well-known ports. The diagram on figure 3.21 shows a flow control, where a sender transmits to a receiver and a receiver gets it, buffer it 1 2 3, buffer here could be like you have a shelf that you can take just maximum 3. Somebody brings 3 luggages, yep, you have a shelf for those 3 luggages. But if you have just 4 availability on that shelf and the person kind of bring 8 stuff, right? Guess what? You can only house 4. Because the buffer overflows, because they can't contain more than 4, right? They're gonna drop the rest of the packages if you run out of that buffering spot. So therefore, TCP uses flow control method called windowing with acknowledgements. This flow control method prevents too many segments being sent at one time and makes sure that the destination host receive all the segments before more are sent. That's why TCP is a reliable network, because he was like, hey, you know what? Before you even bring those luggages, TCP will like, okay, you know what? We've got just 4 spots for you, so don't bring more than 4 items. UDP doesn't care. You bring it, it receives it, and whatever it doesn't, it will just drop it off right away. But TCP will kind of like, hey, hold on, just bring 4 at a time. Or they're going to send you a signal and says, hey, you know what? Or sometimes they can kind of like, if those 4 items get dropped, TCP will go back and try to get it when there's an opportunity to bring more, and he would pick those drop packages. Figure 3.22 shows us an example of that flow. in this case, right, the source sent the first window of 3 segments, and the message indicates 3. See, the destination host receives all segments and acknowledges back a sequence number of 4. And once he acknowledges that is a sequence number of 4, indicating all is good with first group, send the next group. Yep. The source sends the next 4, the next window of segments, which includes section 4, 5, and 6, but packet 5 is lost. See? When segment 5 is sent and received, the destination acknowledges 7 because segment 6 was already received. This prevents unnecessary retransmission. Yep. The 3-way handshake here is very explanatory, right? I talk about the scene arc, and then you connect, and then you start transactions. The 3-way handshake risks transmission and error detection, adds to reliability, but lengthens latency. That's why TCP is not a good protocol for video streaming, because though it's reliable, it takes effort to make it reliable. So if you're streaming video, right, it's gonna be slow. Therefore, applications that do not require reliable data stream service may use UDP, which is the user datagram protocol, which provides a connectionless datagram service that prioritizes time over reliability. That's why sometimes when the network is really bad, if you're watching like Netflix or some heavy videos on YouTube, it will just keep buffering and buffering and cycling and cycling and cycling. Yep. When a computer is getting data for users to use, it's called a client. And when it's getting it from a host that has an application that supplies computers, that's called a server. So that's the relationship between the client here and the server. Connectionless protocol. I think I touched a little bit already about UDP. So it's just very simple. Some of the things the features that you have to know about UDP is that it's a simple connectionless service. It has no windowing. It has no sequencing. It doesn't count package. It doesn't keep track of what it sends and what it has to send in order to complete that package. It has no acknowledgements, which reduces overhead. So it doesn't have that time that TCP does to kind of go back and retransmit because it lost a package among a segment. So UDP doesn't do that. Routing protocols. They simply define the routing function. The first routing protocol is a basic routing protocol. The basic routing here is the router. All it needs to do is to make a routing decision. They care only about network when they are routing, not about individual host IP addresses. Yep. They must know every destination. If a router has a packet to route, but the destination network is not in its routing table, then the packet will be dropped. Yep, it needs to. The information that a router needs to route is not for a router to route, right? It needs a destination address. Possible routes to all the remote networks, the best route or path to a destination network, neighbor routers for which you can learn routes and send data, a way to learn, update, and maintain route information. The diagram on figure 3.24 illustrates a single office router in which router the RT1 has 4 separate interfaces that routes data. That's it, RT1. It has 4 interfaces. You see, FO01, FO, yep, that route. So very simple. You can just read this for a better understanding to know how a single router is set up to route to pass traffic between two hosts. You can read this for better understanding how routing occurs. You can go ahead and read it. Figure 3.25, router with multiple routers. You could also read this to kind of understand how a router is set up, or traffic is set up for routing within multiple routers. In this case, you've got two routers, and each has 4 interfaces, and one of the interfaces of each router communicates between each other. Administrative distance is a weight of value assigned to every type of routing information that a router may receive to be able to determine which source of information is best. Administrative distance is a method, it is a weight or a value that gives a router the ability to be able to pick the best routing protocol, because each routing protocol uses different information to determine its own best path to networks. Figure 3.26 shows a protocol or route source to distance. Dynamic routing. It is a process a router can forward data via different routes or given destination based on the current conditions of the communication circuits within the system. The pros are it saves time and energy, since it must not pass through every router. However, it uses more CPU time and bandwidth. Figure 3.27 shows a routing protocol tree. It is better for us to kind of know, it's advisable to know what the routing tree is, The routing tree comes in play when routers are trying to choose a route. It's very important to consider this in mind for routers. Got static routing on the left, dynamic routing on the right. We've got the IGP, EGP, distance vector protocols, link state, hybrid. You can read that for better understanding. This is not necessarily important for the exam, but it's very important for you to read and understand various details of the various routing protocols. Static routing here just basically gives the router information, whereas dynamic routing breaks into many protocols. You can see how it's broken down to many protocols. Like the interior gateway protocol operates inside of autonomous systems. Broken down, you've got the distance vector protocol, which successfully requires just to know the specific distance and direction to each destination network. They do not keep track of neighboring routes or neighbor routes, since that's the job of the link state protocol. Let's say the link state protocol. They do track changes by broadcasting periodic routing tables. The diagram in figure 3.28 shows the routers in the example network. You can read about routing loops for better understanding of this course. Go into detail and read about the maximum hop count, split horizon, hold downs, link state protocols, neighbor table, topology table, which of course we talked about that, advanced distance vector protocols, external gateway protocols. You can read that for a better understanding of this course. Coming back to touched on the commonly used ports and the various services. You should keep in mind that the Hypertext Transfer Protocol, HTTP or HTTPS, is one of the most commonly used ports. So you might want to just read this and keep that in mind and be able to understand that port 80 is for HTTP and port 443 is for HTTPS for security. File Transfer Protocol. It's important for you to know that the FTP is not secured and was later replaced with the SSH File Transfer Protocol, SFTP, or Secure Shell. Domain name system. It's just important for you to know that a domain name system simply resolves host names. So basically internet names, such as, that's an example, right? It resolves it. And keep this in mind, that domain name system allows the use of a domain name to specify an IP address. Therefore, an IP address can be changed as often as one likes, and no one will know the difference. Keep that in mind about a domain name. Its function is very important for you to understand for examination purposes. The diagram of figure 3.29 shows us the domain name shows us the domain name system hierarchy. The root, which is the dot. The top level domains will give you the .com, the military, the MI for military or navy or whatever, edu for education, org for organization. So in commercial companies, you mostly see them with the .com, or businesses. And military services, you probably see them with the .mil. Educational services, you probably see them with the .edu. And all other organizations, you probably see them with the .org. Second level domain names would be, that's what you see, like for instance, companies. Dynamic host configuration protocol. The DHCP assigns IP addresses to host. What is very important for you to keep in mind here is how that process works. The diagram on figure 3.30 shows us a client-server relationship using DHCP connection. So the first move for a client or a PC to get a DHCP address is they will broadcast to discover if there's a DHCP route, and the DHCP will respond and offer them an IP address. an invitation to treat, which is the offer. Then the client will respond with a DHCP request and says, okay, I've seen what you have. Can you give me an address, please? And the server will respond with the package. So keep in mind that very first step is different from a TCP connection. Because normally with DHCP, clients don't have an assigned IP address. They have to search and ask for DHCP if there's one available. And then they're going to show them the list and then they're going to request. So that first move, you have to keep in mind that it's the client that actually broadcast to discover a DHCP. And you can read this through to kind of get some understanding. Telnet, we've talked about that, which replaces FTP. What is very important for you to keep in mind here is Telnet is on port 23. It's a replacement of just for clarification, Telnet is an application used over the internet to provide a text-based visual terminal type connection. Port 23. It is connection oriented and it leverages TCP to send its control message on the same data path as the data. You might want to keep that in mind. Secure Shell was designed to provide a secure channel from the client to the server. It was not meant to replace Telnet or a replacement for Telnet. Just kind of an added layer of security. Secure Shell provides additional benefits over Telnet. Yep. Because in addition to being a remote command line application, it can be used to remotely authenticate devices. Mail protocols. You might want to keep in mind what SMTP is all about. It defines how mail messages are sent between hosts. Most importantly, you might want to focus to kind of know when does POP, Post Office Protocol, how does it operate? Keep in mind, it does allows downloading mail or pulling it from the server. Get that word. It interacts with the server. IMAP, on the other hand, which is Internet Message Access Protocol, allows downloading mail from a server and it provides a more secure form of authentication. So both POP and IMAP download mails from the server, but IMAP provides more form of authentication. It's more secure because it provides authentication. You can read about the voice conversion voice traffic for better understanding. Voice components. This diagram on figure 3.31 lays down description of IP phone features. You can read this for better understanding of this course. Data signals. Read that. Making a phone call. You read that for better understanding. How it operates, the basic phases. Tear down, call control, distributed call control. But most important, you want to keep in mind that this is voice over IP. That's very important for you to keep in mind. Voice over IP. Yes, we've come to the end of chapter 3. I hope my emphasis will help you in your exams.